Welcome again to another session on Year 12 Maths. This time it's Statistics and Mechanics, in particular the stats portion of the course, and we're looking at Chapter 6, Statistical Distributions. So today we're going to be having a look at how we can represent distributions using diagrams and probability mass functions and tables, and also how we can do some more advanced calculations using statistics, more difficult than we may have seen at GCSE. Before we do that though, of course, there are some warm-up questions as ever, which I need you to attempt, so here they are. So have a look at these questions, jot them down, attempt them independently, and when you're ready to see the solutions, press play, and I'll talk you through them. Okay, so let's have a look now at question number 1. So question 1, we have a table showing the probability of getting a particular score when an unfair six-sided dice is rolled. And we're asked to find the value of k. So we should know here, for any event, that the sum of all the probabilities should add up to 1. And so that's what we can do here. If we add all these numbers together, we should be getting 1. So 0.15 plus 0.2 plus k plus another 2k plus 0.12 plus 0.11, all that added up will equal 1. And so we can see here, k plus 2k, we have 3k. Now to make sure I don't make a mistake with the adding up, I'm just going to check on a calculator. So adding together these values I've got. So I've got 0.15 plus 0.2 plus 0.12 plus 0.11. And that gives me 0.58. So 3k plus 0.58 equals 1. So now we need to subtract 0.58 from both sides. So we get 3k equals 0.42. And finally, if we divide both sides by 3, we see that k, therefore, will have to be 0.14. So that's how we do question 1, and it's complete. So k has to be 0.14 to make all of these probabilities add up to 1, which is what they need to add up to. Let's have a look at question 2. So question 2, again, we've got these probabilities and scores. This time it's for a four-sided spinner, and we're given probabilities that it's going to stop on a particular value. So we're using the information in this table above, we need to complete this table of probabilities below. So we're told that if a score is a 1 or a 2, that's what the 1, 2 means, the probability of either of those scores is 0.1. So we can add in here 0.1 and 0.1. When it's a 3, the probability is 0.3. If the probability is a 4, it's just 0.5. So as easy as that for question 2. So without messing around, let's just move straight on to question 3. So question 3, we've got here that the random variable y represents scores on a four-sided spinner labelled 1, 3, 5 and 7. Given that the probability of being 3 is the same as the probability of it being a 7, and the probability of being a 1 is double the probability of being a 5, and the probability of being a 3 is a probability of 0.2, calculate the table of probabilities below. So this is, as you can see, almost information overload here. So what we need to do is think about what we actually know rather than what we're guessing at. And so the only probability we've been told for definite is this one here. The probability that it's a 3 is 0.2. So we can add in 0.2. Next up, we know that the probability of being a 3 is the same as the probability of it being a 7. So now we know that the probability of being a 3 is 0.2. We know that the probability of it being a 7 must be 0.2 as well. So We know those two for definite. Now we need to look at probability of it being a 1 and the probability of it being a 5. So here, if we let the probability of it being a 1 equal x, and we can get an equation involving this. So if we think about it in this way, so if I call this one x, then the probability of it being a 1, it says it's double the chance of it being a 5. So if that's x, this is only going to be half an x. Okay, essentially this one here is double as big as that one. So actually, I'll just change my mind. I'll call this 2x and that just 1x. So now if we formulate an equation, 2x plus 0.2 plus x plus 0.2, that must all add up to 1, because these four values are all the probabilities for the event, so they must add up to 1. So 2x plus x is 3x, 0.2 plus 0.2 is 0.4, 3x plus 0.4 equals 1. Give myself a bit more space. So subtract 0.4 from both sides. We get that 3x equals 0.6, and therefore x must equal 0.2. And so 2x must be 2 times 0.2, which is 0.4. So probability of being 1 is 0.4, and the probability of being a 5 is just x, which is just 0.2. So that all checks out, and that's all correct. Finally, I did have question 4 here. I'm just going to move on to a fresh slide and do question 4 with all the space I need for it, rather than just having to scrunch it up on the right-hand side. So question 4 says, find the set of values for x such that x squared minus x minus 42 is greater than 0. So quadratic inequalities is always a bit of the syllabus which students struggle with. What I'd suggest here is we're going to draw a graph of this at some point. And so what I'm going to do here, I'm just going to think of this as being a function of x. And so if I just say, think of this as when is y greater than 0, and I'm going to let y equal this here. So y is just the left bit of the inequality. I'm going to draw a graph of x and y, but not quite yet. First of all, I'm going to think if we can manipulate this to make it easier to see what's going on. So looking at quadratics, if you can, it's always a good idea, if possible, to factorize them. So here, we could try and see if there exist two values which multiply together to give negative 42 and add up to negative 1. And luckily for us, there are two such values. The two values which would do that are positive 6 and negative 7. So we can factorize into x plus 6, x minus 7 equals 0. Therefore, the critical values, where they'd be equal to 0, are when x is equal to minus 6 from the first bracket, and from the second bracket, when x is equal to positive 7. So this value here, let's put it there at minus 6, and this higher one, x being 7, I'm going to place here. It's a positive x squared, so this is going to be a happy parabola, if you like. It's going to be U-shaped, so this curve would look something a bit like this. Didn't quite go for that green one, so I'll just make it slightly bigger. And as you can see here, this inequality is true when this is greater than 0. So we want our y, this red bit, to be greater than 0. And you can see, hopefully, but it's going to be greater than 0 for this portion of the curve and for this portion of the curve. So therefore, x squared minus x minus 42 is greater than 0 when x is less than minus 6. Or we can also have it where x is greater than 7, which we had here. And those are our two solutions. So that concludes the warm-up. So now we can get on talking about the main body of this lesson, the statistical distributions. So let's have a look at the next part. Whoops. I'll just get rid of that line, which was put there for no reason whatsoever. So probability distributions. So what does this mean? Well, a random variable, first of all, it's a variable whose value depends on the outcome of a random event. So the range of values that a random variable can take is called the sample space. So the sample space is essentially all possible values that the random variable might be. Although a variable can take any value within a specific range, the outcome is random as it is not known until the experiment has been carried out. It can't be predicted. The random variable is discrete if it can only take certain numerical values, if it's either one value or another value or another value. So it's discrete if it's only got a countable finite number of outcomes. So let's imagine, going back to GCSE and maybe earlier, if two fair coins are thrown. Okay, so if two fair coins are thrown, what could happen? So first of all, we could list all possible outcomes. Now, I'm sure you know there's going to be 4 main outcomes. Both could be heads, HH. The first could be a head, the second could be a tail, HT. Or the first could be a tail and the other one could be a head, TH. Or they could both be tails, which is TT. B, define a random variable x as the number of heads when 2 coins are thrown. And C, generate what's called a probability distribution function in any of 3 ways. So what is a probability distribution function? It is, in essence, a way of illustrating the outcomes. So the main ways of doing it are as follows. So one thing we could do is we could generate what's called a probability mass function. And it looks something like this in this particular case. So what it's saying here is a probability of our random variable taking the specific value little x is as follows. It's 0.25 if x is 0 or 2. So if we've got no heads, in other words 2 tails, or 2 heads, HH, the chance of that happening is 0.25. For example, the chance of getting 2 heads is a half multiplied by a half, which is a quarter, which is 0.25. Same for tails. If you have 1 head exactly, the chance of getting 1 head and the other being a tail is going to be 0.5, because that can happen one of 2 ways. We're looking at this way. Whoops. Didn't mean to have a white pen. It could happen this way, which is 0.25, or this way. So 0.25 plus 0.25 gives us this 0.5 in total. So there's a 0.5 chance of obtaining exactly 1 head. And then the probability is 0 otherwise. In other words, you're either going to have 0 heads, 1 head, or 2 head. If you flip 2 coins, it's impossible to get any other value. You can't get 3 heads if you're only flipping 2 coins. That's just impossible. So that's what a probability mass function looks like. It lists the probabilities in this particular way. Another way it could be done, which is probably the most popular, probably the most common way of representing them, is like this. Simply a table of values, which you will have seen time and time again. So a table of values for this experiment would likely look something like this. So we've got x, which is our random variable, how many heads we get. We can either have 0 heads, 1 head, or 2 heads. And the probability for our random variable is 0 heads is 0.25. The probability that we randomly get 1 head is 0.5. The probability that we get both of them being heads when little x is 2 is 0.25. A third way, which we can do it, which is much less frequent, much less common, is we could do it as a diagram. So a diagram might look something like this for us. So here we've got what x can be, 0, 1, and 2. And the vertical scale, the probability that x is equal to little x, just represents the probability that our random variable is either 0 heads, 1 head, or 2 heads. And notice, if it's a diagram, the bars have to have gaps between them, and that denotes that we're talking about a discrete variable. If they were next to each other, that would be very much like a histogram, and as you should know, histograms are when the data is continuous. So when the bars touch, it's continuous. When the bars are far apart and have gaps in between, that denotes we're talking about something discrete, in this case, a discrete random variable. So these bars should have gaps in between them. Let's now move on and recap a key defining thing about probability, which you've seen already from GCSE. And that is this, that the sum of probabilities of all possible outcomes of any event is always going to equal exactly 1. So using that notation, for a random variable, x, we can write the following. So sigma, which means the sum of the probabilities where the random variable equals any particular certain value, little x, will always equal 1. A probability distribution fully describes the probability of any outcome in the sample space. When all of the probabilities are the same, and only when all the probabilities are the same, it's a special distribution known as a discrete uniform distribution. So for example, if you're rolling a fair die technically, and your discrete random variable big X is the probability of rolling a 1, 2, 3, 4, 5, or 6, whether the outcome is what number you roll, that would be discrete because each outcome is exactly 1/6. So let's now have a look at some worked examples together. So first off, we've got number 1. So we've got a biased 4-sided spinner with faces number 2, 4, 6, and 8, and it's spun. So this isn't going to be a uniform distribution. If it's biased, the probabilities are going to differ. And it says here that the number on which the spinner stops is modelled as this random variable big X. Given that the probability that big X is any certain value is some constant k over x, first of all we need to find the value of k. And so the number which it stops on is big X. And so big X could equal either 2, 4, 6, or 8. So big X could be 2, 4, 6, 8. So the probability that big X is any one of these, well, the probability that it's a 2, because it's k over x, this would now mean k over 2. If it lands on a 4, that's going to be k over 4. If it lands on a 6, that probability is going to be k over 6. And finally, if it lands on an 8, that probability is going to be k over 8. And so, what we've just mentioned before, the sum of all probabilities for any one event will always add up to 1. And so when you add all these together, it should add up to 1. So therefore, k over 2 plus k over 4 plus k over 6 plus k over 8, that should add up to 1. So we've got here fractions with different denominators. What we could do is get these into a common denominator. And we can do that by making each number here on the bottom 24. 24 is the lowest common factor of all these different denominators. So the first one, if we multiply top and bottom by 12, we get 12k over 24. The second one, if we multiply both top and bottom by 6, we get 6k over 24. The third one, if we multiply top and bottom by 4, we get 4k over 24. And finally, if we multiply this one, both top and bottom by 3, we get 3k over 8. And that equals 1. What am I talking about? I mean over 24. Okay, so now that we're all over 24, we can just simply add these numerators. So what we'd have next is 12 plus 6 plus 4 plus 3k. We'd have 25k over 24. So therefore k is going to equal 24 over 25. K is 24 over 25. So next we need to think about writing this distribution in a table. And so here's a table I've pre-made. So what we can do here is write down first of all x, where x is either 2, 4, 6 or 8. Then underneath the probability that big X equals any one of 2, 4, 6 and 8. And so here, when it was a 2, the probability of being a 2 was k over 2. And now we know that k is 24 over 25, we can say here that this one's going to be 24 over 25 divided by 2. 24 over 25 divided by 2, that's going to give us 24 over 50, which would then simplify down to 12 over 25. So this one here would be 12 over 25. When x is 4, this one here, so that's just going to be k over 4, which means 24 over 25 divided by 4. So if we do that on a calculator or otherwise, 24 over 25 divided by 4, that's going to be 6 over 25. When x is 6, that's k over 6. And so now we know that k is 24 over 25. We know that this one's going to be 24 25ths divided by 6. And that would give us 4 over 25. And finally, when little x is 8, that's going to be k over 8. So this one is 24 over 25 divided by 8, and that would give us 3 over 25. As a double check, if you want to, if you were to add all these fractions together, you should get, and you would get, that if we all add up to 25 over 25, 25 25ths, which, as you'd expect, equals 1. Now you've done A and B, you've done the hard work. Part C is actually much more straightforward. So part C says find the probability that x is greater than 2. So the probability of x is greater than 2, that just equals the probability that x is 4, 6 or 8. And so that equals 6 over 25 plus 4 over 25 plus 3 over 25. That gives us overall 13 over 25. Another way we could have done that is the probability of x being greater than 2 is 1 minus a probability that x is equal or less than 2. So we could have done 1 minus 12/25, which would have given us the same as well. Part 2, the probability of x is in between 4 and 8, not inclusive. There's only one way that could happen. That's a probability that x is 6. And that's only 4 over 25. And the last one, sort of a trick question, but not really, as long as you don't panic. The probability of x being greater than 8, well, the biggest value it could ever be is 8. Okay, so this one's actually equal to 0. X is either 2, 4, 6, or 8. Could never be greater than 8. So this one here is actually exactly 0. Let's have a look at a second worked example involving a spinner, this time again. So this particular spinner is spun until it lands on red or has been spun 4 times in total. It says now to find the probability distribution of the random variable s, where s is the number of times this spinner is spun. So just by reading this, we're told here that it could be spun up to 4 times in total. So it's not going to spin any more than 5 times. It can't spin any more than 4 times, I should say. So what we can do now is think about what the table would look like. And so here's a table I've made earlier, which we can now fill in. And so the random variable s is just the number of times a spinner is spun. So if I have here little s is the number of spins, the number of spins could be anywhere between 1 and 4. Now I can think about here the probability that the random variable s equals one of these little s's. So let's think about these in turn. And so what's the probability that it be just 1 spin? So it keeps spinning until it lands on red. So probability that we have just 1 spin is a probability red on the first spin. And as you can see here, if we've got 2 out of 5 sections are red, that's going to be 2/5. So the first one is just 2/5, so we can fill this in nice and easy. Now, to have 2 spins, the probability that the number of spins is 2, that can only happen if the first spin is blue. So blue first, and then red second. Now I've used the word and here deliberately. If you remember the and or rules from GCSE, and would imply we multiply. So that's the same as blue first. Well, blue first is going to be 3/5 chance, and then red second. So multiply would be 2/5. So 3/5 multiplied by 2/5. Multiply the tops. 3 times 2 is 6. Bottoms, 5 times 5 is 25. So probability of having 2 spins is going to be 6 over 25. Now, how would it be where we could have 3 spins? So what's the probability of a number of spins being 3? Well, that could only happen if we have blue, and then blue, and then red. So 2 blues in a row, and then a red. So blue, and then blue, and then a red. So that's blue first. Chance of being blue is 3/5. And multiply by another blue, which is 3/5. And then the third one is a red. Chance of being red for any one spin is 2/5. So we have 3/5 times 3/5 times 2/5. So if we multiply all this out, so the tops, 3 times 3 times 2 is 18. You can use a calculator if you want to, of course. The bottom, 5 times 5 times 5, which is 5 cubed, that's 125. So probability of having exactly 3 spins is 18 over 125. Now, it says here in the question that the spinner is spun until it lands on a red, or it's been spun 4 times in total. And so it can't go beyond 4 spins. And so if it's not landed on a red yet by the 4th spin, we just stop spinning anyway. And so no matter what, if you get to number 4, that's going to be the final spin. So there's no possibility for a 5th, 6th or 7th. And remember, because of probabilities have to add up to 1, this one here must therefore be 1 minus all of these. So finally, the probability of stopping after the 4th spin, probability at number of spins is 4, that's going to be 1 minus a probability that S was 1, 2 or 3. So that's 1 minus 2/5 plus 6/25 plus 18 over 125. At this stage, I'm not going to trust myself to do this on my own. I probably could, but I'm going to use a calculator to be a bit careful about this. So 1 minus, in bracket, 2/5 plus 6 over 25 plus 18 over 125. That gives us 27 over 125. That's the last probability we need to work out, so that concludes all of our probabilities. And so, because a valid way of writing a probability distribution function is as a table, which we've just done, that's fine. If you really wanted to, you could have done a diagram of this, but that would just be, in my opinion, just making life really hard for yourself. The easiest thing, if you can, I think, is just leave it as a table. So that's worked example question 2 completed. Worked example 3. We've got this discrete random variable x, which has the following probability function. And so x can range from 0 up to 3, and the probability that the random variable takes these values from 0 to 3 is given by this function here. And k is just some positive constant we need to find. So first of all, we need to show that k equals 0.25. Well, the first thing I'd suggest to notice here is that it's a discrete random variable because x can only be 0, 1, 2 or 3. So what I'd suggest doing here is a table of values like this and then filling them in accordingly. And so here, when x is 0, the probability of the random variable being equal to 0 is k multiplied by 2 take 0, which is just 2k. When k is 1, sorry, when x is 1, my mistake. When x is 1, it's going to be k, brackets 2 minus 1, which is just k. When x is 2, we're going to have 2 minus 2, which is 0, so k multiplied by 0, that's just going to be 0. And then when x is 3, we're going to have k multiplied by 3 minus 2, which is just k times 1, which is k. Now, when we sum these probabilities, we're obviously going to get equal to 1, because the sum of all probabilities for any one event always equals 1. So as x goes from 0 all the way to 3, the sum of all these probabilities will equal 1. So if we add these probabilities together, which is 2k plus k plus 0 plus k. That'll equal 1. So how many k's do we have? We have 4 k's. So 4k equals 1. Therefore k will equal 1 divided by 4, which is a quarter. But as a decimal, we want to show that it's 0.25. So k equals 0.25. So we've proven what we wanted to prove. K is 0.25. Let's now have a look at part B, so 3b. Show that the probability that x1 plus x2 equals 5, after making 2 independent observations, that this equals 0. So at first this might seem baffling, but if we just return to what we did earlier, we had this in terms of k. Let's now make this numerical and replace any instance of k with a numerical value. We now know that k is 0.25, of course, so 2 times 0.25, that becomes 0.5. K here and there, we can just write 0.25. When x is 2, the probability is 0, so we can fill this in with a 0. We now need to think about how could x1 and x2 sum to be 5. And so x1 plus x2 equals 5. That can only happen when x1 is 2 and x2 is 3, or if x1 is 3 and x2 is 2. We can't have, say, 1 and 4 because it doesn't go up to 4. We can't have 0 and 5 because it doesn't go up to 5. And so x1 plus x2 equals 5 means we want this or that. So we can rewrite this in terms of x1 and x2 being 2 or 3. So for probability of x1 plus x2 equaling 5, that equals a probability of x1 being 2 and x2 being 3, or, now or means plus in terms of probability, means the probability that x1 is 3 and then x2 is 2. So if we work this out now, if x1 is 2, the chance of it being equal to 2, you see, is 0. So this is going to be 0 multiplied by when x2 is 3, which is 0.25. Or we could have, when the first observation is 3, 0.25, multiplied, and, so multiply when x2 is 2. But again, the chance of it being 2 is always going to be 0. So because we can't have an observation equaling 0, but 2 is a necessary requirement for them both adding up to 5, it just can't be done. So we add these together, we get that it's equal to 0. So essentially, the bottom line is it can't equal 0 because that would require x equaling 2 for one event, either the first or second, which cannot happen. So we've just shown here why that is an impossibility. Find the complete probability function for x1 plus x2. So we need to consider the probability function happening once and then overlaying that with a second iteration of itself. So here's what we have for the distribution of x. Then if we combine this with x1 plus x2, obviously it could go as high as 3 plus 3, which is 6. And so we need to now just fill in these numbers. So how would x1 plus x2 equal 0? Well, this could only happen if x1 is 0 so probability x1 equals 0 and x2 is 0. So the chance of equaling 0 is 0.5. So that's going to be 0.5 times 0.5, which is 0.25. So here we're going to have 0.25. The next one, probability of them added together is equal to 1. So here, for the next one, there's two ways that can happen. And so this is going to be the probability for x1 is 0, x2 is 1, plus the probability for x1 is 1 and x2 is 0. So if we add these two together, x1 being 0 is 0.5. That's going to be 0.5. Then x2 being 1 is 0.25. Then it'll be the same value the other way around. 0.25 times 0.5 is the same, so it's just this thing here multiplied by 2 essentially. And so that's going to give us, again, 0.25. This one, if they're both going to add up to 2, for this one, there's actually only one way this could happen. 2 isn't an option, so it can't be 0 and 2. They'd both have to be equal to 1. So this is a probability that x1 is 1 and x2 is 1. So that's going to be 0.25 times 0.25. So this might be one to check on your calculator. So 0.25 times 0.25 is 0.0625. If they both add up to be 3, how could that be done? Well, we couldn't have one of them being 2 as an option. So 1, 2, and 2, 1 isn't going to work. So either one is 0, the other's 3, or the first one's 3, the other one's 0. And so for this one here, that's going to be the probability for x1 is 0, x2 is 3, plus the probability for x1 is 3 and x2 is 0. So that's going to be 0.5 multiplied by 0.25 and plus 0.25 times 0.5, which is the same duplicated. So we're just going to multiply that one by 2, and again what we'd get, that would be 0.25. So this one here is 0.25. Next up, if we're both going to add up to 4. Well, this can only happen, oops, wrong way around, that arrow. Well, this one can only happen if one is 1, the other's 3. They can't both be 2, because 2 is impossible. So this here is a probability that x1 is 1, x2 is 3, plus probability that x1 is 3 and x2 is 1. So if x1 is 1, that's a 0.25 probability. And the other one being a 3 would be 0.25, so it's 0.25 times 0.25. And then it'll be the same value the other way around if we switch from 1 to 3 to 3 to 1. So if we multiply that by 2, that'll give us the probability. So it's 0.25 times 0.25 times 2. It gives us 1/8, which is 0.125. Next one, if x is 5. Well, for x to equal 5, one would have to be 2, the other would be 3. And we just worked out from part B that's impossible, so we can fill in with confidence this one's 0 because of what we worked out from part B. Finally, for part C, how can they both add up to 6? Well, there's only one way that can happen. They both have to equal 3. And so this one here is just going to be the probability for x1 is 3 and x2 is 3. The chance that it's going to be 3 is 0.25. So again, this is going to be 0.25 times 0.25, and that's going to be the same probability as what we had for 2. When we added up to 2, it was 0.0625. So this here will be 0.0625 as well. If you have time in an exam, what would be a good idea is to check that all this adds up to 1, because the sum of all probabilities for any event should always add up to 1. So if we want to check this here, what we can do, so starting from here, 0.25 plus 0.25 plus 0.0625 plus 0.25 plus 0.125 plus 0 if you really want to, and plus 0.0625, you'll see, but it does indeed add up to 1. So that's just proof and a bit of peace of mind that we've not made a mistake, or if we have, it's a very unobvious mistake. So now let's have a look at the final part of this worked example. The final part of this worked example, and this is much easier than it looks, we want the probability that the sum of x1 plus x2 is in between 1.3 and 3.2. So let's remind ourselves of what we had from before. So from before we had this. Now if you notice here, x1 plus x2 can't be decimals. So between 1.3 and 3.2, if you have a look at the actual values it can be, that's a probability that x1 plus x2 between 1.3 and 3.2, that could only be 2 and 3. 1 would be too small, 4's too big. So what this is saying, in a deliberately awkward way to try and throw you off the scent, is that either x1 plus x2 equals 2, or we could have x1 plus x2 equals 3. And so all we need here is to consider the chance of it being equal to 2, which is this, or the chance that it's equal to 3, which is this value. So that equals 0.0625 plus 0.25. So now finally, if we add these together, 0.0625 plus 0.25, we get, as a decimal, 0.3125. A fraction, I suppose, would have been okay, but just to keep it consistent, we've been working with decimals thus far. Let's just keep it in the same theme. We get the probability of that one is 0.3125. And so that concludes the whole of worked example 3. The last one we're looking at, without any surprises, is going to be called worked example 4. This is a bit harder, what students tend to struggle with, so I'm going to talk you through the next one slowly and in detail. So here it is, the tricky final worked example. So we have a bias spinner that can only land on one of the numbers 1, 2, 3, 4 or 5. The random variable x represents the number that the spinner lands on after a single spin. So x is the distribution and big X is representing the particular number. So the probability that the number is r is the same as the probability that the number is r minus 1 for when r is 2 and 5. And also, the probability that the number it lands on is a 3 is 0.2. The probability that the number it lands on is a 1 is 0.1. Part A, find the complete probability distribution for x. I'd strongly suggest doing this as a table. So we've got x that can be either 1, 2, 3, 4 or 5. So let's just label in 1, 2, 3, 4 or 5. Next, let's label in what we know for sure. So for sure, we know that when x is 3, the probability of that is 0.2. So we can add this in, which goes here. And we've also been told that when x is 1, that's got a probability of 0.1. So we can put that here. Now what might throw you is how the next bit has been worded. It's been worded in quite a strange way, this here. So when r is 2 and 5, we've got this thing here. So let's just take it and put numbers in. When we put numbers into this, it will seem easier and more obvious to follow. So the probability that x equals 2, for example. So let's use r as 2. So when x is 2, that's the same as the probability that x is r minus 1, which is 2 minus 1, which is 1. So all it's saying here, in a very fancy, confusing way potentially, is the probability of it being 2 is the same as the probability of it being 1. That's for r being 2. Or if r were 5, the probability of it being a 5 is the same as the probability of it landing on a 4. If r is 5, then r minus 1 is 5 minus 1. This is why this one is a 4 as well. So let's now just see what we've got. So we already know that when x equals 1, that's a chance of 0.1. So therefore, the probability of landing on a 2 must be 0.1 as well, because the chance of landing on a 2 is the same as the chance of it landing on a 1. And so we can fill in that this one is 0.12. By 0.12, I mean 0.1 as well, not 0.12. And then the chance of being equal to 5 is a chance of being equal to 4. So far, we've got 0.1, 0.1, 0.2, that's 0.4. These two combined, therefore, need to add up to 0.6, so that the whole thing adds up to 1. So if these two are 0.6, but they're equal to each other, each one must be 0.3. And so we finally pieced it together and got the distribution. Part B asks us to find the probability that x is less than 3. If it's less than 3, that means we can have x being 1, or we can have a probability where x is equal to 2. So that's 0.1 plus 0.1, which just equals 0.2. The chance of it being a 1 or a 2 is 0.2. Let's now move on and have a look at the other parts to question 4. So next, we need to find the probability that y minus x is equal to or less than 1. So here's what we have. So we've got here that this is what we had before, okay, and we've been told now that we've got a variable y, which is 20 over x, and so this is what it means when it mentions y. Now, weirdly enough, we can solve this algebraically, and I'm going to show you why this works. So even though it's a probability question, this essentially becomes almost like a quadratic. So this is the same as the probability that y, which is 20 over x, minus x, is less than 1. So now, with probabilities, okay, x could be either 1, 2, 3, 4, or 5. So we know x is a positive value. We can now therefore multiply both sides of this inequality by x. Be careful with inequalities. When you multiply through, the sign might switch if you're multiplying or dividing by a negative, but because the possible values of big X are all positive, we don't need to switch the sign because we know we're not multiplying through by a negative. So 20 over x becomes 20, minus x becomes minus x squared, 1 multiplied by big X becomes x. So now let's rearrange this so it's all on the same side of the inequality. So if I subtract 20 and add x squared to both sides, I get x squared plus x minus 20. So this has to be bigger than 0. Now this, you can hopefully see, will factorise. So can I think of two values which multiply together to give negative 20, but when I add them up, give me positive 1? Well, those numbers are going to be a positive 5 and a negative 4. And so there's two ways this could happen. Okay, so if you imagine a graph of this, so x squared plus x minus 20, if I graphed this as a function of x, so if I label big X on this axis, and the y-axis is big X squared plus x minus 20, because it's a positive x squared, it's going to be a quadratic. It's going to be a positive U-shaped quadratic. It's going to have roots where x is equal to minus 5, or when x is positive 4. And so this would have a shape similar to this. And we want it to be greater than 0, which means above the x-axis. So we want x to be equal to or greater than 4, or we need x to be equal to minus 5 or less than it. But like I said before, big X has to be positive, and so this bit here isn't possible. And so what we're looking at in particular is this region of the graph here. And so this is going to be true this whole thing is greater or equal to 0 when x is equal to or greater than 4. So what's the probability that x is equal to or greater than 4? Well, we can see here that means x could be 4 or 5. So 0.3 plus 0.3. So that just means that we need 0.6. That's a probability that this new random variable that depends entirely on x, where y, the probability of y minus x is no greater than 1. And so that might seem very sort of bizarre, but we could almost, until the very last step, ignore the probability table and just focus entirely, almost, on the quadratic inequality. So this often throws students. So what I'm going to try and do now is, in depth, guide you through what's going on behind the scenes, as it were. So what's going on behind the scenes? Okay, so, well, behind the scenes, this variable y is entirely based on x. This is entirely dependent on what x is. So here's what we had for the distribution of the variable x. So now let's think about what the distribution of y would look like. So because y depends entirely on x, the probabilities for the distribution of y will follow exactly the probabilities for the distribution of x. So what I mean by this is, for example, the probability of x is equal to 1 is logically exactly the same as the probability of y being 20, because y in this case would be 20 over 1, which is 20. So it's one and the same thing. This is just a rebranding of the original, if you like. This has just been conjured from the original. Again, if big X equals 2, that's logically equivalent to the probability of big Y being 20 over 2, which is 10, and so on for X being 3, 4, and 5. So from the original, we could generate, if we wanted, a new distribution of what Y is. So if we fill in y next, so I've highlighted here, when big X is 1, that's the same as big Y equaling 20. So X being 1 is the same as Y being 20. 20 over 1 gives us 20, so it's one and the same thing, just disguised if you like. Next along, when X is 2, that's the same as big Y being equal to 10. Like this. So next along, when X is 3, Y would be 20 over 3, which is an exact fraction, just 20 thirds. Best leave it like that than saying 6.67 recurring. 6.66 recurring, rather. So leave it as an exact fraction. When X is 4, Y will be 20 over 4, which is 5. And finally, when X is 5, Y will be 20 over 5, which is 4. And these probabilities will follow exactly based on the original distribution x. So this one will be 0.2, next will be 0.4, sorry, 0.3, and finally, because when x is 5, the probability of that is 0.3, it'll be the same for y as well. So each one of these follows exactly as the original. Next, what we want is this. We want the probability that y minus x is no greater than 1. So let's imagine when x is 1, that makes y being equal to 20. Okay, in that case, y minus x is 20 minus 1, which is 19. So y minus x is greater than 1, not 1 or less. And so this one doesn't satisfy this inequality. We're not interested in this one. So I'll put a cross by it. Let's try when x is 2. Well, when x is 2, that makes y equal to 10. But again, 10 take 2 is 8, which is not smaller than or equal to 1. So again, y minus x is greater than 1. That still doesn't satisfy this inequality. So that's no use. Next, when x is 3, that correlates to our y being 20 over 3, which is about 6.67. So 6.67 minus 1 is 5.67, which is certainly not less than or equal to 1. So again, this is still no good. However, if we move on to x being 4, when x is 4, that makes y 20 over 4, which is 5. And now 5 take 4 is 1, which satisfies this inequality. And so this here, y minus x is not greater than 1, so this one actually works. And so that would work when x is 4. And again, when x is 5, that would make y equal to 4. But we'd have 4 take 5, which is minus 1. Minus 1 is less than or equal to 1. So again, that one works. And so what we want here to satisfy this inequality is this bottom two. So again, we'd want either x being equal to 4, or we could have x being equal to 5, because that forces y to be 4 and makes it work as well. So x being equal to 4, that's a 0.3 chance. When x is equal to 5, that's a 0.3 chance. So again, like we had from doing it algebraically, this gives us 0.3 plus 0.3, which is 0.6. So that's what's going on behind the scenes. I am not recommending you do it this way. I'm just explaining why it works, instead of you being mystified as to how this could possibly make any sense. I hope this helps to explain and illustrate what's going on, as I say, behind the scenes, as it were. It's now over to you to get some much needed practice and mastery with these questions. So, what I suggest that you do is, in the book, exercise 6a, all the questions with a E or a P next to them, or the ones which have an E and a P. The E stands for exam type questions, P stands for problem solving, so these are incredibly important to do, as they are in any exercise in fact. The E and P questions are gold dust. So try all of those on exercise 6a on page 86 to 88. You know the drill by now. Contact me if you're getting stuck, email me if not physically available, or if in doubt, you can even leave a comment in the comment section on the YouTube video. Thanks very much for listening, do consider subscribing, and I'll see or hear from you very soon indeed. Thanks again, and take care.